cover today. Linked list, stacks, queues, and like I mentioned a couple of minutes back, the prerequisite is you should have gone through the introduction to data structure session, which was there. The video was already shared on the meetup. Okay. These are the ground rules. I sometimes speak too fast. Let me know and ask to repeat. If you have any queries, ask. Stop me right there. Send me a message. Speak. Do anything. But please don't let me move forward without with a query in your mind. And even if you're able to understand what we are discussing, please acknowledge. Let us start. Okay, and my handwriting is not that good, and I have not slides prepared. I didn't get time to prepare the slides. So you'll have to work with my bad handwriting. Okay. So this is what we are going to do today. Linked list. Linked list is a physical data structure. Uh, Please keep your mic on mute if you're not speaking. I can see some disturbance coming. Can you guys please keep your mic on mute if you're not speaking? Okay, good. So linked list is a physical data structure. We'll discuss in detail what physical mean over here, but as of now, just for now, remember it's a physical data structure. Okay, and this is a linked list. We all guys have, most of us have already done BTech, and in our college we have discussed there is some structure like this which we call a linked list, right? And what is this structure? Wherein each structure is called as a node, and this is what a node looks like. So linked list is nothing, it's just a collection of nodes. The one node, second node, third node, last node, basically. So each node has got two parts. One part is some data which it is carrying. So this is the data part. The other part is a pointer, or I can say reference to the next node. So basically, I'm just saying that this part is storing the address of this particular node. That is it. So when I say this is pointing to this node, I actually mean this is storing the address of this particular node, or in other words, it's pointing to this node or referencing to this node. Okay, and linked list and the next pointer of your last node is actually null. It's not pointing to anything. There is null stored over here. So by this slash, I actually mean null. Okay, and apart from these nodes and next pointers or references, we all we also have something called as a head pointer. This is the most important part of the linked list. So basically, head pointer gives you the address of the first node in the linked list. Because if you know the address of this particular node, you can traverse the complete linked list and go to all the other nodes. But in case you don't know the address of this particular node, you cannot even move. This is a simple data structure, one of the most simplest and most important data structure from an interview perspective. So maximum questions, rather a lot of questions you can expect from linked list. So it's a very cool and good data structure to learn. Okay. So without wasting much time, let me start with the coding itself. Okay, so you need to write that this is your program, linked list traverse. What you need to do is you need to print all the values in the linked list. So assume this is your linked list, and this is your head. You basically need to print all the values in the linked list. So basically, what I'm expecting is I'm expecting your function to print 3, 2, 5, and 6. Okay. So what do I do? So and this is my input, this is my output. So my return, I'm not returning anything. I'll just print in my function itself. So I'm returning void, and my input is the head pointer, basically address of this particular node. That's it. Okay. Now how do I print? So you guys have any idea? Just take a couple of seconds, couple of minutes to think what we can do and let me know. I really like my classes to be interactive. It's a challenge over Meetup, but then I would expect every one of you to speak up or even comment. Mm, so I'm not getting much responses. Advertising follow the pointed values. Good. So what do I need to do? So basically, I have address of this particular node, right? I need to print 3, 2, 5, and 6. Forget about 2, 5, and 6. Let us just think about this particular node. So I have pointer. I have an address of this particular node, or I have a pointer or a reference to this particular node, and I want to print 3. So how do I print 3? Print head dot data. So this is how I print 3, right? Done. This part is done. Now I need to print 2. That means I need to go to this node, right? So now going to this particular node, I need the address of this particular node. But I don't have the address. But I don't have the address of this node, right? So I don't have the address of this particular node, but the address of this particular node is actually stored over here, right? So I can take the address of this node from this place, right? So assume you have something like this, p is equal to head. So what does this do? It basically creates a pointer over here. So I have address of this particular node in p. I want to move p from here to here. What do? I take the address of this part. So basically I do this. P is equal to p dot next. So what happens if I write this thing? When I write this thing, whatever is there is in this part will be copied to p, right? So suppose address of this particular node was x1, address of this node was x2. So this thing was actually storing x2, right? So when I do this, p was earlier x1, it will be modified to x2. That means, in other words, I can say this link got broken and I have a link over here. So now p is pointing to this particular node, and I want to print 2. And when I print 2, I again move to next node. I move over here. I again print 5. I move to next node, come over here. I print 6, and that's it, right? So that means I need to keep repeating this thing until some condition. And this is an important condition. So your P is over here, you print 2, you move P forward, your P is over here, you print 5, you move forward, your P is over here, you print 6, you move forward, your P is at null, and you cannot print anything. So that means you stop when your P is equal to null. Right? It's a simple one line program. Right? Correct? Got it? Please keep acknowledging if you get it, else or ask doubts, else I'll assume things are going good. Okay. So in the last session we guys discussed a lot about complexity, time complexity, space complexity, blah blah blah. So starting now, whatever program we'll do in our courses in the sessions, we will calculate time complexity and space complexity for each and every algorithm. Is next is a method of P object. Okay, so when I say P object, I think we have discussed this thing in the last session. So I never like to call my references objects. Whenever I write something like node P, I never like to call P as an object. P is not the object. P is just a reference to the object. P is just storing address of an object. So when I do something like this is the object over here. I have a reference. Now this object is this object, this class. So this object has got two parts. One is data, one is next. And when I write p dot next, that basically means go to that object and then get the next value. So basically means go to this object and then get the next value. Okay. So yeah. So I need the time complexity and space complexity for this program. Those who like attended my last session, they should be quick in answering. Linear. The time complexity is linear over here. Linear, or I can write order of n, and that is because the number of iterations for this particular program will be bounded by the number of nodes in the linked list. Right, so if there are 5 nodes in the linked list, this code will run 5 times. There are 10 nodes in the linked list, it will run 10 times. The time complex just linear, where this n is number of nodes in the linked list. Okay. And coming to space complexity is actually it's the extra space which you are creating in your program. So in my program, the only space I have created is this node, this reference, right? There is no other space being created in this program. So that means space complexity is constant over here, order of one or constant. Right? A simple program, good time complexity, good space complexity. Let us move forward. Yeah. So now I want to sorry, not that well. So I want to insert a new node in the linked list. So for example, this is my linked list. I'm again drawing the same linked list 3, 2, 5. I want to insert a new node, and when I say insert a new node, you are even given the data of the new node. So this is what I want to do. So this part is your linked list. After your program ends, your linked list should look like this. Your head should come over here and should look like this, right? Okay, so what do I do? So first of all, I want to insert a new node into the linked list, right? So to insert a new node into the linked list, you actually need to create a new node. And this is how I create a new node, linked list node. So maybe let me name it as P, and I write P dot data is equal to X, right? So just by writing these two particular lines, what I have done, I have created a new node whose data is X, and there is a pointer P, reference P, who is storing address of this object. Okay. So now what do I need to do? Now I have something like this. Now there are two things that I need to do. One thing is I need to make this pointer, this thing. The second thing which I need to do is break this link from here and make that link over here. This is not, wait, this is, and there are two things I need to do. So first of all, I'll do p dot next is equal to head, and I'll do head is equal to p. So linkage is really easy. You just need to visualize these pointers, make try some examples, and you'll be good, right? So by writing these two lines, I'm creating a new node, and by writing these two lines, I'm making those two links. Really simple. And then finally, you return head. There are two ground rules where you're working with linked list, and those are important rules. One is you should always return head, always. So even if you're changing a head or not, you should return head. Second is avoid modifying head. Right? So over here you need to modify head, but unless it is especially required to modify head, should never modify head, right? There are two important rules which we should. Sorry, I'm not that well. There's two important rules which you should follow when you're working with linked lists. Now this program is not that good. Let me try this program in case there is only one node in the linked list, right? So this is my node. This is my linked list, basically head null. So when I write these two lines, I do this. When I do period next is equal to head, this next will now have the address of this particular node. Or in other words, there will be a link created like this. When I do head is equal to p, this link will get broken from here, it will come over here, right? And then you return head. It works fine, right? And whenever you're writing linked list program, there are three things which you should check. The most important thing called as boundary conditions. So whenever you write a program, make sure your program work with the null linked list. Make sure your program works for first and last nodes, and make sure your program works if there is just a single node in the linked list. It's always a good habit to try your programs on these particular three scenarios, right? So let me try my program on the null scenario. Suppose head is null. Suppose in this scenario, right? So in this scenario, what do? I'm creating a new node like this, and then I write period next is equal to head. Now my head is null, so that means this part will be null. And then I'm writing head is equal to p, so that means now this is not there. I'm doing this, and I'm returning head. So basically, it works fine. This is a simple program wherein everything seems to work fine, but this is not what happens when you write other linked list programs. Linked list programs are really sensitive, especially with these three boundary conditions. So if you see, even the time complexity for this particular program is order of one, because there is no loop, no iteration. It will just take a constant amount of time. It does not depend on the number of nodes of the linked list. And just like our last program, this base complexity is order of one. Right? Too simple program. Now let us move forward. Try a difficult program. Now you are given a linked list. You want to delete the first node in the linked list. So I'm again creating my same linked list. This is my linked list. You want to delete the first node from the linked list. So basically, this should get changed to this. Right. So how do I do this? I basically need to move from here to here. And how do I move forward? I do head is equal to head, let complete head. Right. Now, in case you are working with Java or Java or C Sharp, you don't need to worry about this particular object because this will be automatically garbage collected. But in case you are working with C++, you should free this particular memory. So assuming I'm working with Java, this code works perfectly fine. Now again, let me try this code on those three scenarios, especially two scenarios wherein the linked list is null, and the second scenario is wherein there is only one node in the linked list. Right? It's always a good habit to try your programs on these two conditions. I'm speaking this again and again because these are important conditions, and I have seen people missing out the boundary conditions. In case you're in an interview, everyone can write these simple programs. Writing a correct program covering all the boundary conditions is what makes it different from other people. So assuming your linked list is null, when your linked list is null, basically your head is null scenario, right? So in case null scenario, your code comes over here and you are doing head is equal to head dot next, right? And when you do head equal to head dot next, that means this part is null, and null dot this will throw a null pointer exception. So that means even though your code seems to work fine in this particular example, this will not work if head is null. Right? So this is an important thing which you need to check. So that means if head is equal to null, if there is no linked list, don't do anything. Return null. Right? So this is now covered. Let me check other scenario wherein there is only one node in the linked list. Now this is my head. There's only one node in the linked list. My head is pointing over here. I'm coming over here. If head is equal to null, head is not equal to null. I come over here. Head equal to head dot next. Now what is head dot next? Head dot next is null. So basically I'm breaking this link and I'm making head as null. And I'm returning head. So it's fine, right? There was only one node in the linked list that node got deleted. So eventually my head will be null, and which is correct. It's not incorrect, right? So that means now this program seems to work on both of those boundary conditions, and this is a good program, right? So talking about time complexity, space complexity, again, time complexity is order of one because you're not doing much over here, does not depend on the number of nodes. Space complexity is again order of one, no new space created, right? Good. Good simple programs. So we started with linked list. This is nodes, head. It's just a collection of nodes when one node is pointing the next node. And we tried few easy linked list programs, traversing the linked list wherein you just move your pointer and keep printing the data until your pointer is null. Insert beginning, you just need to insert a new node in the beginning. So you create a new node, and then you insert it like this, which basically change the pointers. Right? delete the beginning, you just need to delete the first node. In other in other words, you just move your head to the next node. That's it, right? The time complexity, space complexity, both constant. Now let's try a really difficult program. Now you need to, now this is your linked list, the same example. This is your head. Now you need to insert a new node at the last over here, right? So that means this is not correct. So that means you want something like this. So your last node should now point to a new node which is being created. How to handle if last node is given for deletion? Oh, we'll discuss that. So I started with linked list insert beginning, then I went to delete beginning. I'm doing insert last as of now, and then we'll do delete last. Okay. So so first of all, you want to insert a new node in the linked list, right? So whenever you insert a new node, you basically first need to create the new node. Please pardon my cough. Assuming there is a parameterized constructor. So with this, I have created this particular new node, and there's a p pointer which is saving the address of this new node, right? So now what do I need to do? The first part is done. I've created this new node. Now what do I need to do? Now I need to make this pointer over here. This part, basically this pointer, right? So assuming we have a pointer for this particular node, assuming there is something called as q, which is storing the address of this node, the only thing I need to do is q dot next is equal to p, right? And lastly, since I always return head, I return head, right? So they just go step by step. There's really easy things, not that difficult, right? So now you want q, right? But you don't have q. You have head. You have address of this node. You don't have address of this node. So that means I the only thing I have is address of first node. I don't have address of this node, right? So I don't have this, but I can have this. Now I need to move q from here to here. So basically from first node to the last node, right? In your original linked list, in your given linked list. So basically you need to keep moving your q forward, and this is how we move a pointer forward, right? We discussed even over here in the traversing the linked list. This is how you move forward. You need to keep moving q forward while q is not equal to null, right? So let us try this on this example, right? So q is equal to head, that means q is pointing to 3. Now q is not equal to null, q is equal to q dot next. Q came over here. Again q is not equal to null, q is equal to q dot next. Q came over here. Again q is not equal to null, q is equal to q dot next. So next of this in the original linked list was null. This was the last node. So now q will become null, while q is not equal to null. Now q is null, you come out of the loop, right? But this is not what we wanted, right? We wanted q to have the address of the last node. Your q eventually became null. It's not helping, right? So that means this condition is not correct. Instead of this, you should write something like this. So now I'm not checking whether Q is null or not. I'm checking whether Q dot next is null or not. So when Q dot next becomes null, that will actually mean there is no next node of Q. I'm again repeating when this is an important point, and I've seen people doing mistakes many times over here, and or maybe getting confused. When I write Q not equal to null, that basically means when Q is not equal to null. So this condition will fail when Q will be equal to null. That means Q is pointing to no node, basically null node. Over here in this condition, I am writing Q dot next is not equal to null. So this condition will fail when Q dot next is equal to null. And when Q dot next is equal to null, that basically means that there is no next node to Q. And if there is no next node to Q, that basically means Q is the last node, right? Or you can even try it on an example. I'm really a fan of taking examples and trying out my things, and this is how you should do as well. Even in an interview, it's a good habit to try with an example in the front of interview as well. It's a good habit, right? So Q is over here. Q dot next is not equal to null because Q dot next is showing the address of 2, right? So you move Q forward, you move Q over here. Now again, Q dot next is not equal to null because Q dot next, if this is this is Q is showing address of this particular node. So next of this is showing the address of 5. It's not null. You move Q forward. Q comes over here. Now while Q dot next is not equal to null, right? So Q dot next, that means next of this particular node is null now. So since this is null as of now, you don't move Q forward. You keep Q over here. And this is what you wanted. And then you write Q dot next is equal to P. Basically you join this node. And then you return head. Good. So basically this uh, original linked list gets changed to this. Which is exactly what we wanted. Right? Now again, uh, I stress this thing a lot. You should always try it on boundary conditions. Everyone can write code, but not all people write good, correct code with all the boundary conditions. And it's not that difficult to check the boundary conditions, right? So there are two boundary conditions which are really important. One is when there is no linked list. Second is when there is only one node in the linked list. When there is no linked list, basically means head is equal to null. Right? Let me change the color. Okay. So I come over here, I create a new node, right? And then I do Q is equal to head. That basically means Q will be null now because head was null. Uh, there are two things to answer your question. So I'm answering to Balaji's question. He just mentioned why return head when we should avoid modifying it. Right? You should avoid modifying it, but that does not mean you don't modify it. You many times in your programs you need to modify head. For example, in this program wherein you are inserting a neuron in the linked list, right? At the beginning. So over here you need to modify the head because you are inserting a neuron in the linked list. So obviously your head should now be modified to store the address of this node rather than the previous address of this node, right? So you need to modify head. I'm saying you should avoid modifying head because I've seen people modifying head even in the scenarios wherein it is not supposed to be modified. For example, in this scenario, see over here, right? I've seen people. So you see, whenever I want to traverse, I always take a new node, a new pointer, and I initialize it with head, and then I move forward. Rather than writing this code, I have seen people writing code something like this. While head. And people have asked me this question. So why are you taking a new Q pointer? We already have the address of first node. Why can't we write something like this? While head is not equal to null, head equal to head dot next. People have asked me this question. I have seen people writing code something like this, right? So in this case, what will happen? Your head will, uh, it will come over here, right? Now your head will be over here, and then people have told me, now since you have your head over here, write this head dot next is equal to p, and then return head. Even if you don't return head, they'll say, "Oh, my work is done. I have made that link." So they keep asking me. Then in that case, then why are you taking a new Q pointer, and why do you say that we should not modify head, right? Because the problem over here, my dear friend, is you have lost the address of this particular node, the first node, right? Now there is no place wherein this address is being saved. Now, since you don't have address of this particular node, you cannot traverse the linked list. The only address you have is of this particular node. And it's a singly linked list wherein you cannot move backward. So that means all the nodes before your last node are lost for you. You cannot move backward. So you only have 5 and X. So therefore it is highly recommended you should never change head until it is required for you to change. So that means you should never write code like this. But does it answer your question? And in all the linked list question, it's recommended to return head, because head is the only thing by which you can traverse the complete linked list. So in case your caller does not know, right? So your caller is inserting a new node in the linked list. He does not know the. So you may change the first node as well, right? So in that case, your caller, just by returning him the head node, or in other words, just by returning him the address of the first node, he can traverse the complete linked list. So the only important thing in the linked list is head. This is a bad code. This is a bad code. If you write this code, you'll be out in the first round itself. Right. So I was discussing about the two boundary conditions. One boundary condition is wherein there is no node in the linked list. The second boundary condition is wherein there is only one node in the linked list, right? So I was discussing about this particular scenario wherein there is no node of the linked list. That means your head is null, right? So in case your head is null, your queue will become null, because this is what we have written over here. Q is equal to null, right? So when you have something like this, then you come over here and you see while q dot next is not equal to null, right? So you see q is equal to null over here, and now this thing will be null pointer exception. Whenever you are using, right, yeah, only when explicitly asked you should change the head. Basically, only when explicitly required you should change the head. In case you are inserting a new node in the beginning, then obviously you need to change the head. If you don't change the head, then you are not inserting the node in the beginning, because your head is always pointing to the beginning node. And whenever you write dot uh, in any of your data structures code, especially in linked list, or in any of your programming projects, you guys are working somewhere in good companies. Whenever you write a dot operator, you should think and ask yourself, can this be null? Right? It's a very important thing. Null pointer exceptions are really a nightmare for programmers, and that is just because people are careless, too much careless. Whenever you're using dot operator, just see whether this can be null or not. Right? So over here, this can be null, and this will be null when your head is null, because q is equal to head, right? And this will be null pointer exception. Your null pointer exceptions are the worst thing to come, right? So that means my program does not work in case the linked list is empty. There is no linked list, right? So I need to modify my program. I'm writing my program again over here, because third last. So I have this, a new node, assuming there is a parameterized constructor. So it is always recommended to check for boundary conditions, at least the null boundary condition. So whenever you write a linked list program, make it a habit to first check the null boundary condition, right? So if head is equal to null, right? So assume there is no head. That means there is no linked list, right? So in case there is no linked list, the only thing you need to do is return p. You can either write this or write this. They both are same things, right? So in case there is no linked list, the linked list is empty. That means head is null, and you are inserting a new node at the last. So then that last node will be the first node as well. So that means the address for that particular node will be the head that needs to be returned, right? And then this is covered. So now what I was doing something like this. Node q is equal to head, and then while q dot next. Again, this is important. Why I'm using q dot next over here? You should not learn these algorithms, because if you learn these algorithms, you'll be really confused. You should understand them very properly. Where to write next, where not to write next, and blah blah blah. So by this, you basically move Q to last node, right? And then you do, and this is where basically you are changing the pointers. This is the most important part basically. Everything is important, but this is the more actual part. Q dot next is equal to P, and then finally you return head. Right? So I had two boundary conditions. One is null boundary condition, which is working fine because we've just modified the code. The second is wherein there is only one node, right? So let me try for that particular scenario. So suppose there was only one node. This is my linked list. It looks something like this. I create a new node P. So this is my new node P. So this was earlier null. This was null by default. If head is equal to null, head is not equal to null. I come over here, q is equal to head. I make q is equal to head. That means q is pointing to this particular node now. This is not one, this is null. Uh, while q dot next is not equal to null. So over here, if you see q dot next is null initially itself. So that means q will not move forward. And then I'll do q dot next is equal to p. So basically, I join this link, and then I return head. I return head. Basically, address this particular node. So it works fine, right? This is good. So it works fine, even in this scenario. Now talking about time complexity and space complexity for these programs, uh, if you see the only time we are spending over here for this while loop, all other are just a single statement which are not depending on the length of the linked list. This is just one while loop which is depending on the size of the linked list, right? So the time complexity is order of n, where n is number of nodes, because this while loop depends on the number of nodes. Number of iterations will be equal to number of nodes. And space complexity, even though I have created two new references over here, P and Q, they both does not depend on the number of nodes of the linked list. So I'll still call them as constant. Right? So looks like a difficult program, but not that difficult. Just go step by step and you'll be really good. Right? Good. We'll move forward. So now I have a linked list something like this. and this is pointing to null, and I have head over here. Now you want something like this. This should be what you have after your program ends, right? So again, I'll start with the null condition first because this is what I have been telling you. If head is equal to null, that means there is no linked list. Your linked list is empty. So in case your linked list is empty, there is no last node. There is no last node. Don't do anything. Right? Now I move forward. So I basically want to delete this particular node. So when I say delete this particular node, I basically want to remove this link and make it to null. Alright, so this is what I want to do. And this is how you should proceed. Whenever you are giving a linked list program, you should make an example in your register and then see what do you want to do and how can you achieve. What if you don't have head for the linked list? It's given in your program, right? Do you have head over here in the argument? I didn't get your question. Can you please come again or maybe speak in detail? Okay, you're not providing the head. So what do you have? Oh, I'll come to that. Let me complete this thing first. Right? So you have head as of now, a given head, right? If head is equal to null, return null. That is done. So now the only thing you need to do is you need to break this link, right? Not to break this link, you basically what you need to do is you need to make this link as null, right? Now how do you do this thing, right? So to do this thing, in case I have a pointer over here, the only thing you need to do is this, right? So when you do q dot next is equal to null, your work is done. You have basically removed the last node from the linked list because q over here is the second last node. So now the only task left as of now is to move q to the second last node, right? So these are not that difficult things, really easy and interesting things. You just need to go step by step. So over here, when we were traversing the linked list, we had to move q to over here even after the last node, right? We wanted to traverse all the nodes. Over here, when we were inserting in the last, we wanted q to be at the last node. Now over here, we want q to be at the second last node. And obviously you need to start everything from the start. So you have something like this, and then you do while q dot. So I wrote q dot next not equal to null. When I wanted to move Q to the last node, so now since I want my Q to be to in the second last node, I'll do something like this. Right? Something like this. So let me see what happens over here. So I had linked list something like this, 3, 2, maybe I had 4 as well over here, 5, I had head over here, I started initialize Q with head, then I wrote while Q wrote next dot next is not equal to null, so Q wrote next is basically storing Q wrote next is basically the address of this node, right? And Q wrote next dot next is the address of this node. So this is not equal to null. So I'll move forward. Q comes over here. Now Q wrote next is basically address of this node, and Q wrote next dot next address of this node, which is not null. I'll move forward. Now Curate next is this, and Curate next dot next is the address of this node, which is basically null because this part is null. So I'll stop. So that means when you come out of this loop, your Q is at this node, and this is what we wanted, right? So then what do? You do Curate next is equal to null. So basically you break this pointer, you make this to null, and you return head. Good, works fine, right? So now let me again try it on those boundary conditions. One is your head is null, second is you just have one node in your linked list. Right? Yeah, and we know our program works for null because we anyways wrote the program in this way only, right? In the beginning itself we covered that particular scenario, right? So let me check for this scenario where there is only one node, right? So in case there is only one node, let me change point. In case there is only one node, something like this, right? So there's only one node. So what do? You initialize Q with this, and then you do Q dot next. So Q dot next is this part, and this part is null. So that means this part is null, and then you do dot next. So you're again doing null dot next. You cannot use a dot or a null object. Null reference basically. It will be a null pointer exception again. So that means your code does not work on one node. It's not that rocket science, simple thing, just playing with pointers. So that means I need to specifically handle for one scenario as well, right? Wherein there is only one node in the linked list. So in case there is only one node in the linked list, that basically means head dot next is equal to null, right? Because if your head dot next is null, that means there is no next node to head. That means there is no second node. That means there is only one node in the linked list. So if there is only one node in the linked list, then null, right? Because we wanted to delete the last node in the linked list. There is only one node. That was the last node. The first node was the last node. Your head will now become null because there is no node in the linked list now. It's done null, right? So when you do this thing, then your code works fine. Now again, time complexity for this code, space complexity for this code, order of n, order of 1. Order of 1 because I am not creating an extra space that is depending on the number of nodes in the linked list. It's just a queue. Even if you have 1,000 nodes in the linked list, there will be only one reference created. That means it's a constant space. Time complexity order of n because of this loop. So this loop will run for uh, basically this loop depends on the number of nodes of the linked list. So in case your number of nodes on the linked list are 1000, this loop will basically run for 998 times. We don't worry about constants, so you can say around 1000. So if your linked number of nodes are 1 crore, this code will run for around uh, I mean, around 1 crore times, right? So this depends on the number of nodes on the linked list, and this grows linearly with the number of nodes on the linked list. Right? It's not that difficult program, easy program. You just need to go step by step. Whenever you're given a linked list program, make an example, see what you want to do, check how can you achieve your goal, and then move your pointers to wherever you want, and then change the pointers. So the only thing you need to do is one thing you need to do is check for null scenario. First important part. Second important part. See where you need pointers or references. Whenever I say pointer, you should not come and ask me Java doesn't have pointer. That basically means references. And then move your P or Q, whatever you want to name it, and obviously starting from head. And then change the links. So whatever links you want to change. Finally, return head. Couple of steps, not the difficult steps, easy steps, which ensures that you'll have a correct program, right? So I'm just moving with the slides, uh, giving a 2 second break for each slide so that you can revise whatever we have done till now, and we'll move forward. And I'll take a water break for a minute. Data structures can be learned with any language. It does not depend on the language. I'm using Java over here just for simplicity because I like Java, and then moreover, I'm not using any Java that much difficult Java concepts, right? So you have classes in Python, you have classes in C++, you have classes in C Sharp, you have classes in Java. So whenever I say class, in case you don't know Java, you can treat yourself. You can think of like a class in Python. Hardly matters. Your Python is classes. Your Python has references. Insert beginning, good code, easy code. Delete beginning, simplest code. Insert last. This is the correct one. This is not the correct one. And then delete last. Move forward. So now Ashish asked a question. What if you have a linked list? Though I don't come directly to this question because I usually cover a couple of more programs before coming to this question. But anyways, since Ashish asked, we'll discuss. Ashish or Abhi, I guess. Sorry. The question was something like, or maybe let me create one more note over here. The question was something like you're not given head, right? So that means your program, even though your linked list has got some head, but your program does not have head. Your program is given some node, some reference. You are not returning anything. Right? So assume you are not returning anything. So that means you are given a reference to this particular node, for example. Right? This is what is given to you. And you want to delete this node itself. Okay. So how do you delete this node? One way to delete this particular node is actually doing this thing, breaking the link from here and joining a link over here. Right? So basically, in case you have, assuming you have q over here, you will do something like this: q dot next is equal to p dot next. Right? So that basically mean you're changing this part which was earlier this, now you're modifying it to this basically. So that means there will be a link created over here, something like this, right? Or I can even write this thing like this: q dot next is equal to q dot next. Both things are same, right? Because p is equal to q dot next. Now the issue is you cannot have q because you don't have head. You cannot start from the beginning, right? So you cannot make your q come over here. You cannot come over here. The only pointer given to you is for this particular node. You cannot move backwards, right? And you cannot delete this particular node, right? So the way by which people usually do this thing is not that difficult. It's a little tricky. So how people do it, something like this. They'll do something like this: p dot data is equal to p dot next dot data, right? So when I do this thing, I'm basically changing it to 1, right? And then I'm not deleting this node, I'll delete this node. And I can delete this node easily now. I can write p dot next is equal to p dot next dot next. So when I do this thing, I make a link like this. So even though you have not broken this link, you have simply copied this node over here and broken this link. So eventually, even now, you'll have something like this: 3, 2, 1, 4. It's a little tricky problem. Linked list, one of the famous questions, but it's not that difficult. Right? Abhi, does that answer your problem question? Abhi, no, sure, they is there. What is 4 is given? Okay, so now next code is, what if we have linked list like this? And you are given pointer only for this particular node. And now you want to delete this node. How can you delete this? So in case now the issue is you cannot even copy from the next node, right? Because if you copy from the next node, if you write something like this, where is my pointer? P dot data is equal to p dot next dot data. This part is null, right? It will be a null pointer exception because this p dot next is null. It's a last node. It will be null pointer exception. It will not work, right? And moreover, you don't have queue, you cannot move from here to here, right? So now what do you do? Any ideas? Abhi, you've been asking this question. Do you have any idea how to do it? Okay.
Hello?
P is equal to null. Oh, you cannot do P is equal to null, because if you do P is equal to null, that you are that will basically mean that you are changing this pointer and you are making it null, right? But even then, your linked list is it's intact. So you cannot do P is equal to null. So it turned out this is not possible. You cannot delete the last node of the linked list given pointer just to the last node of the linked list. Okay? This is not that difficult. It's not possible. And yes, I think we are out of time. We share the slide videos. Please give your feedback. I really like the feedback. Please pardon me, but I was not that well today. A lot of cough. Anyways, please give your feedback, be it positive or negative feedback. It helps me to improvise. Please comment on Meetup. Thanks for coming. I could not do stacks and queues. Maybe we'll do it in the next session soon, in the coming weeks. Thanks for joining. Yeah, sure. Please comment on Meetup, be it positive or negative. It really helps me to plan better in the next sessions.